So, functions. Before I give you actual functions like x plus 2 or square root of x, before I give you those, we're just going to look at possible things you would put it and get out of a function. Most functions in this class are going to be you put in x, you get out y. So that's why we use ordered pairs. X is what you put in, y is what you get out. Now, think of all these as terms of what we said earlier, food. For everything you put in, you should get one specific thing back. So, it doesn't really matter how many times you put it in. Like, let's look at number 9. It doesn't matter. Let's say 1 is a piece of bread in our toaster analogy. It doesn't matter how many times you put bread into the toaster. What matters is that every time you put in the same x value, you get the same y value back. Do I get the same y value back when I put in the same x value? No. So to answer, determine whether each relation is a function, this one would be no. It's not. And you can stop there. If the answer is no, you don't even have to go to the second part. We'll talk about it in a second. If you have multiple x values that are the same, if they have different y values, then it's not a function. Because what would happen if you graphed that? If you graphed that 1, 4, 1, 5, 1, 6 on the coordinate plane, well, it's not great, but you get it. The points would be right on top of each other. And that can never happen when you graph these. And we're going to get more into graphing in a second. But that's what can't happen. You cannot have any space taken up by more than one spot vertically. It's something called the vertical line test. You probably have heard of it before. We're going to talk about that in a bit. Number 1. Somebody take a look at that and raise your hand and tell me whether you think that's a function or not. Right. Yes, it is. Now, were there any repeating x values anyway? No. If there's no repeating x values, there's nothing for you to even check. You don't have to worry about the y values because there's nothing that could possibly contradict itself. So, if it's a function, which that one is, you now need to state the domain and the range. The domain is nothing more than the x values that function covers, which is, I think they use like these little squiggly parenthesis thingies. 1, 3, and 5 would be the domain of that function. The range is just all the y values, which are, looks like 2, 4, and 5. And you always put them in numerical order. It doesn't really matter what order they come in. Always put them in numerical order. So your domain, 1, 3, and 5. Your range, 2, 4, and 5. I guess I should specify. So the word relation up here, they use relation for all these because they don't know which ones are functions and which ones aren't. So they just call them all relations. You know, if you have some kind of relationship between x and y, blah, blah, blah. Long story short, they're going to call all these relations. It's our job to figure out if they're functions. Well, number 3, who can take a look at that and tell me yay or nay? All right. Sabrina, what do you think? It's not. Why? Well, these can repeat as long as their corresponding y's are the same. So, no, because their y's are different, they contradict each other. Now, here's the thing. What I was just telling you about the x's, you could have the same point in there 50 times. It could be 3, 4, 3, 4, 3, 4. It's pointless because it's just going to plot right on top of itself. But technically, that doesn't throw anything off because there's not multiple. It's the same thing right on top of itself. So if you were to have the same point, technically it'd be okay because it's giving you the same thing back every time, which was what we wanted. It's like putting, hold on. It'd be like Corey's toaster that only toasts bread. He puts the same thing in every time, gets the same thing back every time. But no, 3 would not be because the y value contradicts each other in both cases, actually. What about number 5? Jessica. Yes, you're correct. How did you know? Yeah, all the x values are different, so the y values are irrelevant. So what's our domain? Yes. That's right, and always try to put it in numerical order. So 3, 4, 5, and 7. What would our range be, Blake? Very Very good. Now, if you have the same thing occurring more than once, you can just list it once. So it would just be -2, 1, and 9. You don't have to write it multiple times. Very good. Number 7. Terrence. Number 7, function or no function? Very good. Very good. And what would our domain be? And our range? Yeah, same thing. Very good. Are there any questions from this slide before we go any further? Okay. All right. Evaluate each function at the given interval. So, functions. Functions, anytime you see, it doesn't matter what the first letter is, but anytime you see parentheses and another letter, that is a function. Now, actually, let me take this off the screen real quick. Most of all of the ones we're going to have in this class, you might notice x, 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 x. Most of the ones we do are going to be x. They don't have to be. This could be a function. Let's just make up some letters. Y of k, k squared plus 2k. As long as this variable is somewhere in here, it's a function. This variable is what you're plugging your number into. So that's, the letters on this side are pretty much irrelevant. The whole reason that they use different letters is this. Let's say I put multiple functions up here. What if I said z of k was 3k plus 1, p of k is x minus 2. Just kidding. K minus 2. The reason they put different letters is so that I can tell you which one to plug it into. So I could say, Morgan, if I plug k equals 2 in for p, which one would you plug that into? Which function? The bottom one, right. Because I said p, that just lets you know this is the function. So these are basically just like ways to label and name the function so that you know which one to look at. So these letters are pretty irrelevant most of the time. The only time you'll ever have multiple is if it wants you to look at a specific one, and the directions will tell you which one that is. And these letters should always match. It doesn't matter if it's K or an X or a Y. As long as the letter in parentheses matches the letter in the equation, that's what we're plugging our numbers into. So, number 27. Eeny, meeny, miny. Caleb, if I plug A, this says plug a 6 into your f function. So you're going to plug a 6 into your x, and what's that going to give you? Very good. 6 times 4 is 24, plus 4 is 29. Very good. That's all you have to do. Go to your function, plug in that number. B, part B, you don't have to plug in numbers. You can plug in anything you want. So they're saying take out x and plug in x plus 1. So what you're going to do is literally everywhere there's an x in that function, you're going to plug in an x plus 1. That's the exact same function, but instead of x, I plugged in x plus 1. Now what's the only thing I have left to do here? Yeah, simplify. Distribute your 4. And what does that simplify to? Yeah, 4x plus 9. Very good. What about part C? What do you think we need to do there? Austin, Flower. What do you think we need to do for part C? Yeah, just plug in negative x. 4 times negative x plus 5. So that'll be what? Negative 4x plus 5. Let me simplify it. End of story. Sometimes your x won't go away, like in notes. Good. Let's look at 31. 29 looks pretty much the exact same thing as 27. Actually, we'll look at one part of 29. Part A. When I plug in negative 1, let me ask you, is that going to be 1 squared with a negative, or is that going to be negative 1 squared? Right. That's important to know because this one will be positive, and this one would be negative. So, remember, whenever you're plugging something in for x, you need to plug the whole thing into the x. So that would actually be a positive one for you to work with. Let's look at 31. Who wants to venture a guess what part B is going to be in number 31? or how we would go about solving that. How do you think we're going to go about doing part D on number 31? Yeah, just plug it in. Again, our variable won't go away. We're just kind of switching variables. So I'm going to plug 3a in for every x. Very good. And yeah, now you'll need to distribute it. What's 3 to the 4th? Anybody know that stuff today? Nice. 81a to the 4th. What's 3 squared? 9. There you go. That is this simplified. 3 to the 4th, a to the 4th, 3 squared, a squared, and then 1. Good. Good. All right. Now, these. I just told you a second ago by what me and Michael were doing when we were doing our example of what is function and what's not a function. I told you the square roots were technically not functions, and that was true. But in order to make them more function friendly, just like he answered me in the first place when I asked him the square root of 9, when you are doing a function of a square root, you do just take the positive, because if you took both, it wouldn't be. So you were actually right with that. When you plug something into a square root function, you are just going to take the positive number. So, who can tell me part B of 33? What's that going to end up being? Yeah, like a 10 in, so it'll be 16. Square root of 16 is 4, plus 3, 7. Very good. What about part C? What's that going to reduce down to? Or who can tell me how to work or what I can do to work for that? Yeah. So it'll be square root, well, really good my one thing. Square root x minus 6 plus 6. Technically you put that parentheses, so it gets plus 3, the 6 will cancel, and you're left with the square root of x plus 3. Right? Take it down as far as you can, and then you're done. Take a second to look at 35 and 37, or even a piece that we've missed, and raise your hand if you'd like to see a certain one work. If it's different from something we've done, or think maybe it'll work out a little differently. Look at all the parts of 35, 37, any other problem on the board, and let me know if there's parts that you want to see. 37, absolutely. So I'm going to plug in r squared for every x. All right. Well, we have to do this. What if r squared was just over r squared? What would that reduce to? 1. Now, I'm going to ask you to use a little logic here. What does an absolute value do? Make this thing positive, right? Can you square anything in the... Can you square any number and come up with a negative number? Think of a number you can square and get a negative number. A real number. Is there one? No. So that absolute value kind of turns out to be useless here. So you could still reduce this to 1. Although if you were to have left it like that, that would have been fine. I just want to see that you know where to plug it in. If you have a few questions on the reduction, that's okay. We can talk about that more later. I just want to see r squared over absolute value of r squared. And if you write 1, I'll give you the reduction. That'll be fine too. But you don't have to do that. Other questions from anything you see on the board? Well, yes, was whatever's underneath the radical. Where are you looking at? 33, yeah, and we started to say, let me take that elsewhere. We'll look at that. You're absolutely right, Austin. I even mentioned that when we did it. I probably shouldn't have, but I skipped that step because that parentheses is going to end up just going away anyway. But you're correct. So that would have been square root, parentheses, x minus 6 plus 6 plus 3. You're right. I skipped that because I saw it was eventually just going to go right away anyway. Parentheses are good if it's going to affect your order of operations. Like if there was a square here, like say that had been r squared in the original problem, then it would really be important because you would need to know to FOIL this before you do anything. But I skipped that step because there wasn't being any. Well, I mean, how do you know the 3 is not in the original? It's not in the original. They would have drawn it further. Other questions? Good question. Alrighty, let's move on then. In exercise 39 through 50, graph the given functions f and g in the same rectangular coordinate system. Blah, blah, blah. What they really want you to do is plug in all the values from -2 to +2 and plot those 5 points for all of these. So I'll pick one. Well, let's start with the basic one. Let's start with 39. You're going to have to make multiple XY charts. So here will be my f of x XY chart. Well, actually, the technical way to do this. When you're dealing with functions, your y value, like, let's say I were to say, what is f of 3? That means plug in 3 for x, right? Yeah. And what's that going to equal? When you plug 3 in, whatever that equals, that's your y. So, most of the time in function notation, 3, like for this right here, 3 would be the x that I'm plugging in. And whatever you get back, that's going to be your y, which sometimes they just denote as f of 3. So this is what you're plugging in, and whatever you get out is just going to be what, when you plug 3 into this, whatever you get back. So my f of xy chart is going to look a tad different.
Excuse me, teacher, if there's any sophomore wanting a schedule change, you need to go to the bottom of each building at this time. Sophomore, if you need a schedule change.
Alright. So we're plugging in -2 to 2 for both. So when I plug in -2 to 2 into my original, well, it's just x. So I'm going to get the same thing right back. So it'll be -2, -1, 0, 1, and 2. Oops. When I plug it into my second one, I'm going to be adding 3 every time. So -2 plus 3, -1 plus 3, 0 plus 3, 1 plus 3, 2 plus 3. Before I go any further, are there questions about where I got any of those numbers? All right. Which part? I used these because it said from -2 to 2 in the direction. That's why I just standardly put these in. That's what you're going to plug in from. And then these just came from their specific function. f of x. I plugged in -2 into that. Got this. -1 into that. Got this. I plugged all of these in here into f of x and got these y values. But because it was just x, it just.
Well, where did the b come from?
Well, there's 2 of them. See, they want you to plug it into both functions. That's why I have 2 xy charts.
Okay.
Yeah, that's a completely separate function. And then I plug these into g of x, and that's where these came from. -2 plus 3, -1 plus 3, 0 plus 3, etc. Good question. Any other questions? All right, we're ready to graph them. You do not have to write multiple graphs. In fact, I would really prefer you do them on one graph because I want you to see how these are going to be affected. We're going to do a section here in just the next few days where all we do is graph, graph, graph. And you're going to see how these things move around. All right. So, first one, -2, -2. -1, -1, 0, 0. 1, 1, 2, 2. That is my f of x. My g of x, -2, 1, -1, 2, 0, 3, 1, 4, 2, 5. Let's see. Once you have obtained your graphs, check. Describe how the graph of G is related to the graph of F. How would you describe the difference in those two graphs? They are parallel. But if I said you're on blue, how would you describe how to get from blue to G? How much? 3, yeah. You'll go up 3 units. Now, not all of them will be quite that simple. Some of them you'll be like, well, it has to flip and move down 1, but we'll look at those when we get to them. All right. I'm going to do 49 for sure before we're done, but look at 41, 43, 45, and 47. Which of those would you most like to see first? I can work them all if we want, but what's one you really want to see? 41, 43, 45, or 47? 47, okay. Oh, darn it. 47. All right, XY chart time. X, f of x, x, g of x. All right, so I'm going to plug in, once again, -2 to 2, because that's what the direction said. When I plug those values into f of x, Joey, what are my y values going to be? Excellent. And if I plug those into g of x, Colton, what are my values going to be? Very good. There you go. 10, I think. I think you only squared it. That's right. So very good. All right. Again, before we go any further, are there questions about where they got those numbers? Yes, sir. Do you understand why I chose these? Okay. Then these came, I plugged these values one at a time into the f of x function. -2 cubed was -8. -1 cubed was -1. That's where all those came. And then we did the same thing with this function. -2 cubed plus 2 was -8 plus 2, -6. -1 cubed plus 2 was +1. We plugged these into the g of x function. All right? No problem. Good question. Questions, questions, questions. Love them. Shows me you actually want to know this stuff. All right. -2, -1, 0, 1, and 2. Ooh, 1, 2, 3, 4, 5, 6, 7, 8. I only need to, oh, dang, I have to go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. f of x, I'll do in blue. -2, -8. -1, -1. 0, 0. 1, 1. 2, 8. Again, these aren't perfect. They're just sketches. That is f of x. G of x, I'll do in green. -2, -6. -1, +1. Maybe I should have chosen a more contrasting color. 0, 2. 1, 3. And 2, 10. So, last step, you have to write down, or in this case, just describe to me, how would you describe the difference between the green dots and the blue dots? Eeny, meeny, miny, Olivia. That's right. It moved up some. Was that the exact same thing we had a second ago? They were just moved up? One thing that you're going to start noticing and that we're going to do a whole section on, notice what happened. We added 3, they moved up 3. We added 2, they moved up 2. Those little patterns are going to stay pretty consistent. Just a guess, what do you think 41 is going to do? Notice, -2x isn't changing. What's the only part that changes? minus 1. What do you think is going to happen there? It's going to go down 1. What do you think is going to happen on 45? It's going to go down 2. Yeah. Little things you're going to start to pick up on, and that's good. 49, these are annoying. I think they just want to see if they can trick us. I'm not even going to bother. 49, XY chart. Is there anywhere to plug, is there anywhere to plug in a value? No. That means those Y values are going to be the same all the way down. Negative 2, 3, negative 1, 3, 0, 3, 1, 3, and 2, 3. When you graph this, do you think that's going to be a function? No, because your graph is going to look like this. Oh, I'm sorry. Yes, it will be, because there's no repeating it. Sorry. It's going to look like this. Boom, 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 boom. It's going to go straight across. That was my mistake. It is a function. I was thinking this way. And for g of x, what do you think all those y values are going to be? 5. So it's going to be up here. So the ones without letters are actually the easiest. They just look different, so we think they're hard. Questions about anything you see on the board? About what you're going to need to do or anything? Excellent. Does anybody need me to leave this on the board for a second? Alright. Oh, wow, big directions. That usually means we have to do a lot of reading. Graph the given square root functions. All on the x values. Dang it, let me just read the directions. Graph the given square root functions, f and g, in the same rectangular coordinate system. Use the integer values of x to the right side of each function to obtain... Y'all can read. Read that to yourself and we'll talk about it. Okay. Basically, all it says is you're going to do the exact same thing here that you did on the last page. Only difference is they gave us different x values to plug in. Instead of negative 2 to positive 2, they gave us these. Why do you think they chose these? Who has a theory on why they chose these numbers specifically? Yeah, they're nice, even, perfect squares. So that when you take the square root of them, you don't have to deal with any decimals. So you're going to do the exact same thing you did over there. And once again, going back to the example Michael and I did earlier, they're saying just take, I don't remember where it was, just take the positive one. Oh, the sign to be greater than or equal to 0. Just take the positive square root of it. That way you can just graph it so that it doesn't upset our function. So you'll plug all these into this one, 0, 1, 2, and 3. F of x. 0, 1, 4, 9. When you plug those into the function, you're going to get 0, 1, 2, and 3. Then I have to do the same thing for my g of x function. So that'll be negative 1. Square root of 1 is 1, minus 1 is 0. Square root of 4 is 2, minus 1 is 1. Square root of 9 is 3, minus 1 is 2. And then it becomes just like the last one. Graph this one, describe the difference. What do you think the difference is going to be? It's going to go down 1. Nothing changes. This one will be a little different. What's the difference? Just looking at like the way the equations are built up, what's the difference between this one and this one? Now, critical thinking moment. I'll give you a hint. This one's not going to go down 1. How do you think this one's going to shift? It's not up and down. It's going to go horizontal 1 unit. But you'll see that when you graph it. But you're going to do the same thing. You're going to plug these values into this one, these values into this one, and graph. Okay. Is there a specific part of what's on the board right now that you have a question on? It's just the same as the last slide. The only difference is it's square root. No? Okay. Then we're going to move right along. Almost. Remember I said earlier, the problem with those functions is you had y values overlapping each other. And that's, again, raise your hand if you've ever heard of the vertical line test. Oh, good, so I don't have to describe it that well. Good. Basically, if you can drag a vertical line across your function and never have it hit a spot more than once, it's a function. That's a function. As I do it on this one, notice I hit multiple times in multiple places, not a function. So, function, not a function. What about 63? Function. It doesn't matter if there's a gap. All that matters is if you hit something more than once, which we don't. It's just one all the way across. What about 57? What about 61? Yeah, the only one on here that wasn't a function was 59. Vertical line test. Just drag your pencil across. If it touches in multiple places, then it isn't a function. Use the graph of x to find each function's indicated value. Kind of a lengthy section. Essentially what this says is, remember I said you're going to plug in x and get back y? You're going to plug in x, so where is x equal to -2? What's my y value if I move function at x equals -2? So 65 would be -4. 67 would be what, Savannah? +4. 4, 4. And what would 69 be, Jordan? That's right. -3, 0. Questions about where we're getting those numbers? If you're not understanding why I'm pointing certain things, raise your hand and I'll set it. Okay. 2 more slides. Oh, it's just the same thing as the last one. Find g of negative. All the difference is it's not f, it's g. 71. Colton. Very good. 2. 73. Sarah. What? You can't really tell, can you? Yeah. Why do you think it was 2? That's right. You can pretty much look. The arrow implies it's going to stay here, so that means over here it's going to be 2 as well. You know, one of the last things we do this year is just like that. There's going to be missing parts of the function, and it's going to say, what do you think it's going to be? But it's going to say it in mappy words. And it just wants you to say that. And for some reason, people tend to struggle. Here's what it's going to be at the end of the year. I'm going to remind you of this when the time comes, that it's literally, it'll be something like this. There'll be a gap. And they'll be like, what do you think it's going to be at x equals 0? And you just look at the context clues and figure out, what do you think the y value is going to be? 0. So, hopefully you remember that. That'll be limits. It'll be one of the last things we do this year. And I'll remind you back to the second day when that seemed so easy. And it still should be. That's the whole point. Okay. 75. Now, this is worded a little differently. Notice, it's not giving us a number to plug in. What's it giving us? The number that it equals, which is the same as which value? That's the y value. So they're saying, for what value of x will your y value be 1? -2. Very good. That's where your y value is 1. Question. Great. Almost done. I know what you're thinking. No, more slides. This is fun. Okay. Oh, wow. All right. All we have to do is just list several things. We have to state the domain, the range. You know what? We'll start tomorrow with this. This has been a ridiculously long section. We're going to start with that tomorrow. So I'm going to cut this. Oh, just kidding. This part off of your lesson. EOE means every other even. So you'll basically count by 4s. 2, 6, 10. You'll do every other even. 28, 32, 36, 40, etc.